Hello, and welcome to Data Understanding and Visualization in Python for Beginners, Part 2. In Part 1 of this series, we basically discussed some of the basics of NumPy and Pandas for data manipulation. In particular, we basically started NumPy by using arrays, by creating arrays from lists and tuples. We then talked about dimensions and shape and the accessing different elements in multidimensional arrays. We also talked about some of the useful functions available in NumPy, including a range function, the random module, and reshape function. Then we talked about the slicing in NumPy, and we also discussed the difference of slicing in NumPy and the ordinary lists in Python. Then we discussed basically masking, or sometimes called the fancy indexing, in NumPy, and we discussed how this kind of indexing differs from the ordinary slicing in terms of creating a copy rather than a view. Then we talked about broadcasting and some other universal functions in NumPy, and we then switched our discussion to pandas. We start discussing pandas by introducing series object and some of its properties, including values and index. And then we switched our discussion to a two-dimensional or spreadsheet-like object in pandas, which is called the data frame. We discussed certain characteristics, certain properties of the data frame, and we saw how we can index different kind of data, columns, rows, or submatrices inside the pandas. We discussed also some possible source of confusion using implicit or explicit indices in pandas, and we encourage to use LOC functions or ILOC functions explicitly to mention whether someone is interested in implicit index or explicit index. We then talked about some missing values, how to handle missing values, how to fill the missing values, and we also talked about the operations that can be performed on all the data values in a data frame. We also saw concatenating multiple data frames together, and then we talked about the group by function in data frame. That's very, very powerful function in arranging the results, sometimes summarizing the results, sometimes just ordering and arranging the results in a particular desired way. And then finally we apply some of these concepts on a CSV file. Basically we actually run some of these functions on adult data file that was available on UCI machine learning repository, publicly available data file. We actually read that data file, we do some processing on that. Primarily we converted at least one text field to one hot encoding numeric field, and then we saved that file to another CSV file, just for an example. In this particular video, or in this particular part of the series, we are going to talk about visualizations that are available in Python. Basically, we'll be discussing primarily we'll be focusing more on Matplotlib. That's a very powerful package in Python for visualizations, but we will also be discussing its comparison with Seaborn, and for interactive plotting we will be discussing Bokeh as well. Although there are other ways, there are other packages for plotting as well. Even the plotting can be done directly from pandas. I mean, pandas has its own plot functions, its own scatter matrix functions, and a lot of plotting support is available inside pandas as well. But in this particular video, we'll be actually focusing more on basics of Matplotlib, Seaborn, and Bokeh, and the discussion of in-depth plotting through pandas and also through these kind of packages will be deferred to our full-fledged course on AI sciences, where we have explained all these things in a greater detail. So let's start by package Matplotlib. So basically we have this Matplotlib package already installed inside packages. And this one function that is much more important in that, although there are so many, is pyplot. So one way is to just import this matplotlib.pyplot as PLT. That is kind of standard. There are a lot of styles that we can use for in Matplotlib. The styles, the graph styles. Here I have used this one, but there are so many others. Then there are two important functions. One function is figure that actually handles that actually acts as a container to hold all different kind of plotting objects inside, and another kind of function axis returns an object ax or axis plt.axis class object that actually handles all the x-axis, y-axis, and box kind of representations inside the plot. So let's go to our friend Jupyter, and let's just get started with this Matplotlib. So let me just yeah. So let me first import matplotlib.pyplot as PLT. Let me do that. And then there are so many styles that are available. So let me see what kind of styles are there. So style dot available, yeah. So let me just print those. I guess I have made certain spelling mistakes. Yes. So there are a lot of styles that are there that are available. For example, BMH Classic, dark background, fast. A lot of those, and one can prefer one style over the other in certain situations. For example, here I'm going to use a style, for example, plt.style.use. That use function allows you to which kind of style I'm interested in. So let's say Seaborn white grid. So let's say this is the style I'm going to use. And let's draw our first basically plot, the empty plot. Let's just plot our first figure by having this, and ax is equal to plt dot axis, and this actually shows our very first figure that has nothing in it. So yeah. So all the contents inside that will be handled by a figure object, and all the boxes and bounding boxes and axes, they will be handled by this AX object inside. So yeah, so that's our very first plot. So let's dive into some more interesting plots in Matplotlib. So let's generate some data point and apply some function on that and see how can we. So let's import NumPy that just to generate some data as np. Just import that, and now let's say we have x equals np.linspace, generate points starting from, let's say, 0 ending at 10, generate, let's say, 1000 points, generate those many points, x, and y is, let's say, simply np.sinx. Let's say these are my y values. And now what I do is I basically generate figure as plt.figure. Come on, that's a function, and ax is simply ax plt.axis. And then what I do is ax.plot, that's my function, x comma y. So this basically gives a very first plot that is available to you. So remember, I have called this plot function from AX object rather than the FIG figure object. Rather than using this figure function separately or axis function separately, you can have the same kind of thing directly from PLT. So for example, let's say you have this data XY available. Let me regenerate this data. And then you simply use plt.plot, and the same thing happens. Sometimes working with figure object independently and axis object independently become more fruitful but you can just use plot function directly from PLT and you're just good to go about that. So that's our very first plot. Next, let's move towards, plots, multiple plots. Maybe we can have many more plots on a single plot. On a single figure, maybe we have many more plots. So we have X, Y. Let's generate a Y2 as well. And let's see, oops, what happens. Yeah, Control C. Let's just move to our next figure. And let's say this is my Y1. And let's say I have Y2 as well. So Y2 is simply np.cos x, let's say. And then what I do is I plot Y1 separately and I plot Y2 as well. And the same thing, both of the things, they will get plotted on the same plot. So that's the plot that is available. Yeah. So even if you have more plots, for example, if you have Y3, let's say Y3 is equal to, let's say, Y1 plus Y2, let's say that's your Y3, you can have that plot as well. So plt dot plot xy3, and automatically it will be having a different color, and you can have several plots on the same figure. Yeah, great. So you can, and you can have the axis object, and you can do the same stuff using the axis object as well. So next, we talk about some of the styles that are available. For example, there are several colors. Here you have seen the colors are assigned automatically. This blue color, this green color, and this orange color, they are assigned automatically. However, you can actually specify the styles yourself. You can actually specify the colors yourself. So for example, let's take an example. plt.plot x values already generated, y values of y1, let's say, already generated, and let me specify that I need the color for this particular plot to be blue. And then plt.plot, for example, xy2, and you set, okay, the color for this particular plot I want green. So you can specify the whole green yourself, or you just write the G letter, and that means green by default. And you can have, for example, plt.plot, and you can specify the color for the third curve, maybe in a tuple, RGB value. All the values are between 0 and 1. So for example, 0.5, 0.8, and let's say 0.4. That might be in RGB values for the color. So the color, you can specify color in full strings, their initial letters, tuples of RGB, and there are other ways of specifying these colors as well. So now you can see, so the colors we specified here actually more resembles to green. Let me reduce the green component. Let me reduce the green component to 2, and maybe you get a different color. Yeah, cool. So now you have a blue color, you have a green color, and you have some color whose RGB value is this. These are not just the colors. You can specify the line styles as well. So for example, if you want, for example, here all the lines are solid. They're connected solid lines. What if you want the dashed lines? The plot, they appear in as a dashed line. So for example, plt.plot, you go for, let's say, x, and let's say x plus 1 maybe, and you say, okay, my line style that I want is should be solid. In that case, the line style will be, oh, well, what's the problem? Here is, I got some line style. Oh, yeah. So that's a solid line. If you, for example, change it to dashed line, for example, here, dashed line, then it will appear like in a dashed way, this way. And if you change, for example, this to dash dot, dash dot, and then you will get dashes, then dots, then dashes, then dots, and so on. And by the way, I mean, this can be anything. Maybe this can be Y that you have just seen earlier. You can have these dashes and dots. Wow, why not? And maybe you can have just the dotted line. I mean, just the dotted one. So dotted, all the dots. So dash, dots, solids, and then you can have these color properties. You can write, okay, color is let's say green, and so color properties there, these properties. So you can use both of the properties in combination. And there are shortcuts as well. Rather than writing all these dotted and dashed and all that stuff, you can just specify, for example, you can go and specify, okay, I want a dotted line. So for dotted, you just write a colon and you get the dotted line. If you want solid, for example, you just write the hyphen symbol and you get the dotted line. If you want a dash line, you just write the hyphen symbol again and you get the dashed line. If you want a dash dot, you write first dash and then dot, and you have this particular thing. You need not to actually specify the colors separately either. You can have, for example, plt dot plot x, y, 1, and you just say, okay, I need a solid green, and you will be having a solid green. Or you can have, for example, a dashed red, then in that case you will be having a dashed red. Or you can have, for example, dotted plot with cyan color, and you can have a cyan dotted. Yeah, I mean, a lot of things. Or you can have a dash dot, why not? You can have a dash dot in color. Let's say the color is black. So black is specified by K. So yeah, so you can have a lot of styles. You can have a lot of colors, all these combinations with very smart kind of commands. And you can have multiple of those. For example, if you have PLT, you can have multiple plots and different kind of styles and colors together. And you want here, let's say, dotted green, that is there. And then you have PLT dot plot x, let's say y3, and you have, let's say, this one as dashed, let's say red. And yeah, I mean, all these things in a single plot with different kind of styles and colors that you have specified. Yeah, so I mean these things are available. Not just these, you can set the limits. You can set the axis limits, for example. For example, you want your axis, rather than going from, your axis right now is going from 0 to 10, and that may be because the x you have generated is between 0 to 10. You can set your axis yourself. So for example, you can just write here plt dot x limit, and here you can set the limits of your axis. For example, -5 to 15. These are the axis limits. And now you can see the plot actually starts from -5 and go to 15, because you have set the axis to start from -5 and 15. But because there was no data point that was there in this particular area, you're no longer seeing any graph there, but you can set the axis if you want. Further, you are seeing that the y-axis is going from -1.5 to 1.5. You can set that as well. You can say, okay, plt dot y limit, for example, let me go from -3, let's say -3 to 2.5. So you can do that as well. In that case, you can see your plot. I mean, it looks like that. In the area of interest, you have a lot of plots, but inside because you have extended your limits, you can just you have just wasted some of the space here, but maybe that may be required for certain kind of intuition or stuff like so. I mean, who knows? We can have another command. For example, let's say let me go into the next plot. We can have some pre-specified properties as well. For example, plt.axis, that's a function axis, and if we give in this particular axis, if we give, let's say, tight, that means x-axis and y-axis, they both should be tightened around the values that are actually there inside the data. Not just tight, we can have equal, equal, equal. That means x and y, they should be plotted to just match the aspect ratio of the screen and stuff like so. So sometimes these tight and equal, they may equally required. I mean, they may equally required. There are other tricks as well. For example, you can reverse the plot just by reversing the limits. For example, let me plt.plot, let's say x and y1, and let's say the color is, let's say x and y1, and I want that all as dash dotted, let's say red. And then what I do really is I actually reverse the limits. What I do is plt.xlimit, and I say, okay, go from 10 to 0 rather than 0 to 10. And what it does is actually reverses the graph along x-axis. Not only that, if I just reverse the axis, these limits, just limits, in y-axis as well, for example, go from minus 1.5 to minus 1.5. The whole graph will be flipped upside down. I mean, like you have taken the reflection of it from the origin. I mean, you can just specify the limits, x limits and y limits, and you get really the different effects and results altogether. We can actually annotate the graphs, for example, by specifying here some string that represents the x label. We can specify here some string, for example, that represents the y label. We can set the whole title of the figure. If we have multiple plots, we can specify the multiple plots with respect to their labels. So all these, let me give you an example to do all that kind of stuff. So let's see, plt dot plot, let's say x comma y, x comma y1, and let's say this plot I want really is in dash dot red, and this plot I just call this plot as, let's say, sin x. Let's say this is that plot. Next, let's say I have plot x comma y2, and I want this plot as solid green, and let's say the label of this plot is sin x, cos x. That is cos x. Cos x. Oh, why this is green? Oh, yeah, that's fine. So plt dot plot, let's say x comma y2, y3, let's say, and let's say this is dotted black. This is dotted black, and let's say the label or the type of this particular plot is, let's say, sin x plus cos x, let's say. And what I really do is, what I do right now is I basically, let me set the axis as tight, maybe. Let me set these axes to be tight. Maybe I can specify the limits by myself, but I can do that as well. Plt dot title. What should be the title on top of the figure? Let's say sin and cos plots. Let's say that's my title. I can set the label on x-axis label, let's say label, let's say I call that as x. I can set the label on y-axis as well, let's say plt dot y label, that is, let's say y. And what next? Let me set the legend as well, plt dot should I specify this y, or should I call it as sine x, cos x, and maybe sine x plus cos x. These are, because these are my y values. Let me just show you that, and things will get clear. So legend command will actually specify these kind of labels in these kind of styles to know which curve represents what. So yeah, so let me run this, and you can see a very fancy plot here. Yeah, so let me zoom it down so that, yeah. So now you can see the x-axis label got this x, y-axis label got this whatever string we gave it, and the title, this is the title of the figure, and here this particular pattern is for sine x. Remember this we gave as a label here. Whatever the label string is, that will be printed. So that's the sine x here, and that's the cos x in green, and the dotted black is basically sine x plus cos x. So we can annotate our graphs as no problem. I mean, and many times this annotation basically is required. Further, I need to also specify some of the differences between PLT functions that can be used and the axis function that can be used. For example, let's say let's say fig is equal to plt dot figure, and let's say x is equal to plt dot axis. By the way, make sure that when you make this axis object, this is ax ex, and when you set the axis limits, that is ax ix. So be careful. I mean, maybe you just switch those two and you get horrible kind of results. So focus on e and I, the difference of e and I. Now let's say we have ax dot plot, for example, x comma y1, and then we can have ax dot, for example, set x label, let's say x, and similarly we can have ax dot set y label, and let's say that is y. So we can have this particular thing, and we have this x label and y label available. Equivalently, as we saw earlier, we can set these x and y labels using PLT as well. But in particular, in some of the cases, for example, when we talk about x label and y label, we cannot use directly ax dot x label as we have used plt dot x label. For x label and y label, we have to use the set underscore prefix there. Although other functions, for example, x limit, y limit, and title, if you use set x lim, set y lim, set title, all they work the same as in ax. Not only that, we can apply a set function in general, and we can set a lot of properties by applying the set function in general. Although the same kind of thing can be achieved from PLT as well, but using this axis object, we can do the same stuff as well. So let's see, ax is plt dot axis, and then we have ax dot plot. Let's say xy1. Let's say I want that to be dashed red. Okay, so then I can set ax dot set, and then I can set a lot of properties here. For example, I can set x limit to be 0 to 10. I can set, for example, y limit, that's a property, to be between, let's say, -2 to 2, or maybe I can set the x's to be tight or stuff like so. I can set the x label as any string, let's say x or anything, let's say, I can set the y label as whatever string, whatever descriptive string I want. Not only that, I can set the title as well here. That's my title. So I can do all that stuff. Oh, there is some error. Yeah, here is the error. Yeah, title is this. So now you can see each and everything is basically, so you can use the access object, or you can use the pyplot plt alias at the same time, and everything works just as it is. Next, we discuss a lot of different kind of markers that are available. For example, maybe we want, rather than this continuous kind of plot, maybe we want some scatter kind of plot. I mean, the plot that just represent, rather than these dashed and dots, maybe there are other symbols that are available. Just take, for example, we have, let's say, plt dot plot x y1, and we just say, okay, my marker is just the points, and the colors are, let's say, black. In that case, I'll be having a scatter plot. This is no longer scatter, and the reason is there are a lot of points there. So let me generate a few points just to show you that this indeed is a scatter plot. So x is np dot linspace. Let's say start from 0 to 10. Let me generate just 20 points, and let's say y1 is simply np dot sin x. So now if you see, I have these kind of all these points that are available, just like they're not connected, and they act like a scatter plot. Although PLT has a scatter function itself, but you can use these different markers to just get the kind of look and feel that you really want. And there are several markers that are available. For example, if I just played a dot there, it will print all these markers in dot. If I print this, for example, X there, that's a different kind of marker with all the X's. If I print, for example, here a plus, that's again a different kind of marker. All the points are displayed as plus. I can have this, I mean, there are so many markers there. I can have this V, for example, and that is the triangle, this kind of triangle. I can have this, let me show, yeah. I can have this uppercase, for example, this power symbol, and I can have the triangle up with the top corner up. I can have this kind of triangles. I can have this kind of triangles. I mean, so many of them. And I can have this squares, or I can have these diamonds. Yeah, so I mean, so many of them. Let me just play with all these kind of markers that are available. Let me just write a program to actually show you some power of using this different kind of markers together. So let's say we have this marker array, marker list markers, all the markers. Let's say we have these. Let's write all the markers. Let's say O, that's a marker. We have dot, that's a marker. We have actually comma, that's also a marker. We have, let's say, X, that's a marker. We have, let's say, are you seeing it properly? Yeah, should I? Yeah, should I? I guess I should zoom it up. Okay, then we have this plus, that's a marker. Then we have, for example, this V, that's a marker. This sometimes used as a power symbol, that's a marker. We can have another marker, for example, this kind of triangle. We can have a marker like this kind of triangle. We have squares. We have diamonds. Yeah, so let's have these markers available. And what we really do is we generate, let's say for markers in markers, what we really do is plt.plot np.random.rand. Let's generate x-axis just by random 5 numbers. Let's generate the y-axis by random 5 numbers, and let's say 5. And then what kind of marker we are going to use is M, and label is simply label is also M. So let's do that and see what happens. So you see that, oh, we haven't applied the legend. Let's have legend at the end, plt dot legend. So yeah, I mean, these are all the legend. The legend is available here, and here you can see all of them in different kind of colors, different kind of markers, all the random data. Yeah, so yeah, I mean, you can use here I have just plotted the data just randomly, but I just want to show you that we can have, for example, all these kind of stuff available, or we can use any kind of labels at any time. We can use any kind of markers, any kind of colors. I mean, we can have lists of colors, arrays of markers. We can use these dynamically in loops and stuff like so. So they are really powerful. I should also mention here that this is not just the markers that actually specify the scatter kind of plots. You can actually PLT has its own scatter function. So for example, PLT dot scatter, that's a function. So xy xy1, I guess. What kind of data set I have generated earlier? xy1, yes. So xy1, for example. And if you want color, for example, color here. So let's say color is red. The size, if you want different sizes, so size might be, let's say here I have size, let's say 50, and if you use alpha blending as well to see through, let's say that is this 3, and you can have a lot of color maps. So here we have color map, for example. If I use the color map as where ID is, yeah, so also I can have a color bar available if I want to. Just do, yeah, so I have all these colors. I have all that thing available. That is my color bar. That's my scatter plot. If I just change the size, these points, they will blow up just on a larger size. I can have different kind of colors. I mean, I can use, for example, a color just as let me show you really. The colors might be just to use, let's say np.random.rand, let's say colors 30. Let's use the random colors, and sizes, maybe I can use the sizes as, let's say, the random sizes depending upon let's say 100 times np.random.rand. Let's say 30 of those, because I have 30 points. I can use random sizes for different kind of points, and random colors. And in that case, the plot, oh, oops, there is some error. Let me see what kind of error I have done. Color keyword must be MPL color spec or sequence of color specs. Yeah, I mean, I have not used, maybe I have done something wrong. Oh, if I have to use this multiple colors, I have to use C rather than colors. Oh, so yeah, I remember that. I have to use C rather than color if I have to use a list of colors. So I guess it should work now if there is no further bug. So let me see that. So now, if you have seen, it's a cool kind of plot with different sizes and different colors on different, and these are the color bars that are available. If you really want to know what kind of color, what kind of color maps are available here. We have used this particular color map. There are a lot of color maps. For example, plt dot, let me just check, cm dot all. So these are all color maps. So you can see there are so many of them. So many of them. Different. You use different color maps, you get different kind of results there. Yeah. So there are a lot of color maps here. So I have used simply just I've used here. I have used this particular color map. Yeah. So if I for example increase the value of this alpha, you will see more kind of solid colors rather than opaque of those. So now you can see those. Yeah. So, and further, you can have multiple plots again on the same kind of regime that we have seen earlier. So that was about scatter plots. Let's see also just an example of contour plots as well. Because we are just moving towards plotting in a bit detail, let's see some contour plots as well. Just to show you also the power of plotting, and another changing the color map, how it affects basically all the visualization. So let's say we have x as random and p dot or linspace, for example, generate some points starting from 0, ending at 5, generate let's say 50 of those. And let's say we have y as let's say np dot linspace, generate some points, let's say starting from 0, let's say ending at 5, and generate let's say 40 of those, 40 points, equally spaced points. And then we can have xy as a mesh grid, np dot mesh grid xy, that basically generates all the grid starting from this x and y. See, we have 50 points starting from 0 to 5. So maybe the first point is 0, then the second point maybe is 0.2 and stuff like so. Then we have independent y points, but we need a grid of those. So for example, if we just, oh, I have an error. Wow. Linspace. Maybe I have used some spelling mistakes here. Oh, this E is not there. Yeah. Yeah, sorry. So now if you see this X basically is the idea of mesh grids. Let me give you the idea of mesh grids. Just let me reach. Yeah. The idea of mesh grid is, let's say you have this particular x is, let's say this is 1, 2, 3, and 4. Let's say just 4 points in x. And let's say the y is, let's say 0, 2, 8, and 7. Then what mesh grid does is it actually make different points with 1 and 0, that's 1 point, 1, 0, that's 1 point in xy space. Then 1, 2, that's another point. 1 with 0, 1 with 2, 1 with 8, 1 with 8, and then this 1 with 7, then this 2 with 0. So you can think that as a Cartesian kind of product. I mean, it makes a whole grid centered at these kind of points. And on these grids, you can define some function. For example, the function might be simply x plus y, or it may be some arbitrary kind of function. And then you can see the contours, where the contours just actually are the values where the function has the same. What are the input values where the function output is the same? So for example, if this is the output of the function, if this is the z value, for what pair x and y the z values have the same value. Those levels where the z values are same, they are called contours. And in PLT, there's a contour function alone. There's a contour fill function designated by this f. So let's see that. Let's see that in Jupyter Notebook just to see how cool that is. So let's actually plot this function. So let's say we have mesh grid now available. Let's say z is 10 steric np dot sine x plus let's say 2 steric y, let's say that's our z. And what we really do is we plot plt dot contour fill x, y, and z, make 20 intervals, equally spaced intervals, and set the color map as RD GY. There are so many color maps. Let's say this, and also plot the color bar as well. So color bar. So let's see what happens. Oh, you see that? I mean, these are the contour plots. How cool is that? Oh my God, that's awesome. Let me show you that. Yeah. So these are all these curves. I mean, the curves with the same kind of color. They specify the value of x and y, where the z value is the same. So we can have, for example, plt.x label as x, plt.y label as y. Maybe this should be a string, x and y. And we can have a title as well, plt.title as contour plot. So now if you see, we can have a little bit annotated plot with this. This is my x, this is my y. The total number of intervals, if you count, they are 20. If we reduce this value from 20 to down, you will be seeing less intervals. For example, here you see only 10 intervals. Yeah. So if interval means the whole x space is divided into how many intervals to make these contours. Similarly, the y. If you increase that value, let's say from to 30, you will be seeing more fine-grained intervals and more kind of continuous switching between different contours. Yeah. So yeah. So that's the contour plot. Okay. Next, we talk about Seaborn. That's a very high-level plotting library built on top of Matplotlib. So one thing that you must notice, or you must know, that all the visualizations that you can achieve in Seaborn, they are achievable in Matplotlib as well. But several times, due to really high-level interface of the Seaborn, you can achieve certain kind of plots, certain kind of visualizations much easier in Seaborn as compared to Matplotlib. Although you can do the same stuff in Matplotlib. Seaborn itself is built on top of Matplotlib, so Seaborn is not going to give you a functionality that is beyond the reach of Matplotlib, but it is going to give you an interface that in certain kind of plots, it will be much easier to use Seaborn rather than Matplotlib. Further, this Matplotlib and Seaborn, they can be used in combination, that we will see shortly, to achieve very beautiful kind of visualizations. Another thing that SNS, or this Seaborn imported as SNS alias, it actually gives the layouts, the axis layouts that are very beautiful and much more appealing and engaging as compared to the default or the available axis styles and in Matplotlib. Although Matplotlib recently is also increasing its styles to follow these kind of styles in Seaborn, but Seaborn has really cool kind of these styles, default styles. So let's say let's start with just a simple comparison of this Matplotlib and Seaborn. First of all, let's import Seaborn as SNS. Let's import that. So that's imported. So plt dot style, let's say dot use. Let's use a classic style just to give you a look and feel of difference between the style of this Matplotlib and Seaborn. So let's generate some data just for a simple plot. Let's say np.linspace. Let's start from 0, end at 100, and let's generate maybe 1,000 points. Yeah, so that's x. Let's say y is simply, let's say, cumulative sum of, again, the random numbers, random dot rand n, and let's say these are 1000 by 5. So let's say these are 1000 by 5. So these are basically five vectors. Let me just show you the shape of y. It is basically 1000 by 5, and x is just if you see the shape of x, sorry, I should write that x dot shape, that is basically 1000. Now you have x and you have y. Y are actually, you have 5 outputs against x, just we have generated randomly. Let's use plt dot plot simply x and y, and let's use the legends. Let's say legend. What kind of legend we really, let's say the legends are A, B, C, D, and E. Let's say these are the legends. How many columns you want the legend to spread on? Let's say 2. And what should be the location of your legend? Let's say the location of legend is upper left corner. So if you see that, you will see this kind of plot. Let me scale it properly so that you can see the whole plot. That's the plot with classic layout. Let us just change simply the layout and keep everything else the same. Let's just simply change the layout. We are going to use the layout from Seaborn, the default layout, and we will see how the plot looks like just with that. So let's say, so let's set the layout. For example, sns.set, it will set a layout from Seaborn. There are several layouts, but I'm setting a default one. And now you will be seeing the plot just because of the layout. It looks like much more engaging than the plot you have just seen on the above. Again, I'm not saying that this kind of layout is not available in Matplotlib or you cannot achieve that. You can do all that stuff, but Seaborn actually gives you kind of one-liners to achieve these kind of cool and engaging plots. Not only that, I mean, you have cool functions for displaying, for example, densities and histograms and all that stuff. So, for example, let's just display certain histograms in Matplotlib first. Although we have set the layout, and then we will see how to actually display the density plots using SNS KDE plot function. So let's just go through with some of the histogram plots in Matplotlib. So let's generate x is, let's say, np.random rand n. Let's say, let's generate 5,000 points. And let's say all these points has standard deviation not 1 but somewhere with a factor of 50. Let's say y is let's say 200 np.random.rand n. Let's say these are also 5,000 points, and let's have a z as well with again the variance or the standard deviation smaller than y, random.rand n, and let's say these are also 5,000 points. And let's say this particular z is not centered at origin, but it rather is shifted 500 units to the right. Now let's say plt.hist, let's say x, where density is true. If you do not set this density true, the histograms, they will not be up to a scale, and one histogram may dominate the other in the scale. So it's always good to display the density to keep the scale and the area under curve as 1. So alpha is 0.5, let's say, just to build the opacity. So next we can have this plot for y and the plot for z. So we can have a plot for y as well, and we can have a plot for z as well. So let's say now if you see that these are the density plots. Let me just zoom in. So you can see now these are the density plots available by Matplotlib. We can have the density plots, for example. Using these are the histogram plots. Also, we can have the density plots, the curves that actually approximate the probability distribution of all these. And let's use a density function from Seaborn library, which is the KDE plot. Let me first build a data frame out of these three columns that we just have right now. Let's say data is pd dot data frame. I have imported pandas earlier. Yeah, no. I guess we have. So we should have import. Even if you have not, we should import that now. Import pandas as pd. Let's say data equals pd dot data frame, pd dot data frame, and let's say we have data frame with x, or maybe okay, the name is x and the value is x. The second column is y, and its column entries are in y. The third column is z, and its values are in z. You can have these different names. For example, you can have this a, b. You need not to have the same kind of names, and then c maybe. Yeah, that's your data. Once the data frame is generated, what you can do is, for example, you can iterate over the columns of the data in data dot columns, and you can have plt.hist as before, but now you will be iterating over for each column of the data, and maybe you want a density plot. The area under curve must be 1, and maybe you use some alpha blending with 0.5 maybe. And on top of that, you can have, for example, this KDE plot. The KDE plot basically is kernel density estimate plot. That's a continuous approximation of probability function that can be approximated from the data. There are a lot of ways to calculate the densities. One way is to use the kernel density estimate. There are others as well. So let's see how the plot looks like. Oh, there is some error. What error? Yeah, there is some error. A rectangle object has no property alpha. Okay, so misspelling again. I guess I have spelled everything. I messed up with spelling. A-L-P-H-A, alpha. Yeah. So that's alpha. Now let's run that code, and we can have this plot that looks extremely cool. Let me set the zoom level so that you can. So the histograms as earlier as before, but these density plots or the continuous curves, they're actually showing the continuous distribution function for each of the columns individually. I should mention here that you can have these kind of plots directly from the data frame. There are ways to plot directly the pandas object, the columns, but that we will be discussing in our actually comprehensive course related to this data understanding and visualization. Here in this particular tutorial, I'm just going to talk about the Matplotlib, Seaborn and Bokeh. But these kind of plots, they can be achievable directly from the pandas data frame as well. So now if you see the kernel density plot, that is much cooler than earlier. And this is not, by the way, this is not the only way to plot these kernel densities. You can have, for example, the Seaborn actually gives you further functions to plot these densities in more fine-grained form. For example, there's another function called dist plot. So let me go for that for column in data dot columns, and let's say SNS dot dist plot, distribution plot for each data column. And here you need not to specify anything, just do that. And if I just show you that plot, that is much cool and nicer than you have seen earlier. Here, for example, these are the distribution plots. So you can use KDE. You can see the difference between KDE, and you can use the dist plot for distribution SNS. Yeah, so moving forward, we can have, for example, we can have joint plots as well, where you want to see the joint distribution of two different columns or variables in a particular data frame. And not only the joint distribution, you may want to see the individual distributions on top. And let's see what I'm talking about. Let's change the SNS axis style to, let's say, white. That's a cool style for what I'm going to do, just for that. And we can have SNS joint plot, and joint plot has, let's say, the variables A and the variables, let's say, B. These are the two variables I'm talking about this data, and what kind of plot I'm really interested in. On top of the x's, I want the density estimates on top of the x's. So it may take a while to complete. So if you see here, that's a much cooler plot. Let me just show you that in a proper scale level. So that's the axis A. That's the axis A. Let me show you that. This is axis A and this is axis B. So this is all the data in column A. The distribution of the column A, the kernel density of column A is there. The distribution of column B is there, and the joint distribution basically is here. So the darker the color, the more distribution inside. The fairer the color, the distribution is vague outside, or just I mean, in the center you can see here the peak is in the center. That means the color is darker. As you move away, these are kind of contours. If you move away from the center, the distribution just falls down, and that's what it looks like. Not only A and B, you can have, for example, between C and B, you can have that distribution as well. So whatever pair of data points you just want to see. Here you can see the plot looks like a little different. In C you have, for example, this is the range from 0 to 900, and the density is again normal. Here for B, the density is normal, and again the same stuff. So yeah, so that's, and you can further place legends there and place labels there, and you can annotate this a lot the way you really want to do that. Next we talk about one more very powerful feature of this Seaborn library, which is pair plot. There are so many powerful functions in Seaborn library, but this one is really cool. I mean, this pair plot function. So before actually introducing this pair plot, let me just load some classification data just to show you the power of this pair plot. So let's load this iris data that is available in SNS dataset. So iris, the dataset is also available in scikit-learn.dataset module or packages. That is also available there. So that's our dataset. Let's see if the dataset is loaded properly or not. Yes, it is loaded. So iris.head, for example, let's see, 60 values, and these are all the 60 values. So it has 4 features: sepal length, sepal width, petal length, petal width, and species, and all that kind of. And obviously we have for different classes the different kind of classes are these species. So let me for example give you iris dot species dot unique values. So it should give me the unique values. The classes are setosa, versicular, and virginica, and the total number of data points here are iris dot shape. For example, if you see, so there are 150 data points, each with the 4 features, and the fifth value or the fifth column basically represents the class label. That's a classification data. We can also see the columns here, and the columns basically are sepal length, that's a feature, sepal width, that's a feature, petal length, that's a feature, petal width, that's a feature, and so on. What if we want to see the distribution of sepal length and sepal width? What do we want to see the scatter plot of sepal length and sepal width together? And not only that, we want to see that distribution with respect to each species. So for example, for each kind of class, there are 3 classes here, setosa, versicular, and virginica. With reference to each class, I want to see the distribution or the scatter plot of let's say sepal length and sepal width. Not only this pair, I want to see the distribution or the relationship, basically the dependency, visual relationship between sepal length and petal length. I also want to see the relationship between sepal length and petal width. Maybe I want to see the correlations between different features. And what if I want to do that for every pair possible? And for every pair possible with respect to each class, how can I do that? Well, I can write a code here and we can do that stuff. But here is what is available from SNS. Just a simple command, sns.pair plot Seaborn. So pair plot, and we just give iris, and then we specify what is the class, what is the feature that, what is the column that should be used as a class label, just to separate different colors together. And if you now run this, you'll be see extremely cool plot here. Yeah, so let me show you that plot by just scaling it properly. So yeah, so here you can see, for example, this first of all, you see that the 3 different classes, they are given different colors. So blue is for setosa, orange is for versicular, and virginica just got the green color. You can just see here the sepal length and the petal width, they both have this kind of relationship with respect to each class, which means if you just use these 2 features rather than all, you may get very good distinction. Here, sepal length, for example, this column is all the sepal length with all the other features. For example, sepal length with petal length, sepal length with sepal width. Here you can see sepal length with sepal width actually mixes virginica and versicular together. I mean, the 2 features, if used just alone, may confuse the 2 classes if you use just these 2 features for classification. On the other hand, if you see, for example, here in this particular plot, if you see the petal length and the petal width, they actually separate the 2 classes very beautifully. Also, you have on the same kind of diagonal, you have kernel density estimates or the kernel density plots for each particular class individually. Yeah, so I mean, this is really powerful feature. The same kind of feature is available also in Panda's plotting library called the scatter matrix. Yes, we should also know the Seaborn function for that, because it is just one-liner and extremely powerful to basically achieve a lot of cool stuff like pair plots. And even if you have, for example, I mean, hundreds and hundreds of features, it will be able to plot all of them, the pairs of all of them. How cool is that? Yeah. So next we talk about, let's say, some 3D plots that are available. Although I can talk more about this Seaborn, and we actually have very comprehensive discussion in our full course. Let me switch now towards some 3D plottings, three-dimensional plot. What really a three-dimensional plot is when you have, for example, the variables have, when you have, for example, two variables. Let's say this is x, this variable is x, and let's say this variable is y. This may be some feature, maybe let's say sepal length in iris data maybe, and this may be another feature, maybe petal length in again in iris data, and you may want to be interested in some value that is a function of x and y. So for example, let's say the z value is simply x plus 2y, or maybe x squared plus 2y. In that case, if I supply the x value as 0, for example, and y value as 4, let's say, then what will be the z value? The z value will be 0 squared plus 2 times 4, and z value will be 8 at that particular location. Z value will be 8. Similarly, I can go through the whole this grid. For example, 0 with 4, 0 with 3, 0 with 1, 0 with 0. I can search for whole this 0, and then I can move to 2, and then I can say, okay, 2 with 4, 2 with 3. So I can make all the ordered pairs of using this kind of x values and y values, sometimes called the mesh grid. I can use that, and I can compute the value of z. Now for each pair, for each ordered pair in x and y, the value of z is basically the height that is basically leaving this plane of x, y. So consider this is x and y, that is a plane, and the height at a particular location, for example, at this particular x and y, the height is actually the value of the function, or the value of the z at this particular pair of x and y. The height may go in the other direction if the value of z is negative. So these kind of plots are three-dimensional plots, and they're very, very handy. And we are going to use this three examples of these three-dimensional plots here. One thing that you must notice here, that we will be using again Matplotlib, plt.figure, and axis. When we generate axis, we will be primarily generating this figure.gca, the current figure, and we will talk about the projection 3D. There are other projection modes as well, but we will be talking about 3D. Let's make these wordings concrete in Python. Let me go to Python and actually code something for you. Just you can see this particular kind of plot that we've just seen in the slide. So let's, for example, import matplotlib. Maybe we just need to import some of Matplotlib toolkits. So let's say toolkits.mplot3d, import that from this kind of toolkit mplot3d, import access 3d. So import that. I guess that's imported. Yeah. We already have NumPy, we already have PLT imported, so let's import this particular thing for 3D plotting. So let's have a figure, let's say plt.figure, let's have access ax as figure.gca, gca is just the current figure, and we fix the projection type to be 3D. So that's our projection type 3D. So the environment for three-dimensional plot is basically set. That's the empty three-dimensional plot. If you see, I mean, nothing is there, but it's a three-dimensional layout that is set for you. So here you can have X label, you can have Y label, and you can have Z label. So let's, for example, set ax dot set X label, for example, X. And here now you'll be able to see this is the x-axis. Similarly, you can set the other labels as well. Maybe ax dot set y label as y, and maybe you can have ax.set z label as z. So that's the empty plot that is available for you. Yeah, so that's the plot. Annotated with x, y, and z, and you can see here, I mean, the look and feel is really three-dimensional. I mean, all that stuff you're seeing here. So let's plot some data on top of that. Let's generate some data and plot on top of that. So let's generate some data. Let's generate, for example, let's say we have some value. Let's say we have some radii, just going into polar coordinates. Let's say we have some radius or r value. Let's say lin space. Maybe start from -2, go till 2, generate, let's say, 100 points, and whatever you do, take a square of that and then just add 1 to that, so that R will be a NumPy array with 100 values in this particular format. Now next let's generate for example maybe x values. X is basically let's say x is simply r sine theta. So sine, so what is theta? Let's generate a theta as well. So some theta, that just to make a circular plot, let's generate a theta here. So theta is, let's say, np dot lin space, go from -4 pi to 4 pi. For asterisk np dot pi, and generate 100 points. So that's theta. Let's say x is np dot sine theta, and y is, let's say, again r np dot cos theta, maybe. Yeah, so then z might be, for example, the same np dot lin space, like we did in r radius. I just, let's say, from -2 to 2, and let's say we have 100 of those points. So let's say that's our z. And next what we do is we say, okay, ax dot plot. We need not to set this as, already we have done this projection as three-dimensional, so we need not to specify anything. We just call the function plot as it is, as we called earlier in two-dimensional case. The projection 3D will handle the 3D plottings. We can set the label if we want. Label is let's say 3D, let's say 3D plot. That's our label. We can also have the legend. So let's say ax dot legend. So legend will be set automatically. Oh, what's the problem here? Oh, I have not entered the string here. So now if you see, you'll get a very cool plot here. This kind of plot, yeah. This is the plot. Yes, so that is kind of the plot. Here you have seen the this is the x-axis, this is the y-axis, this is the z-axis. I've just generated some parametric curve out of it, and that's basically a 3D plot. So the crux of the story is basically this projection 3D. Once you have this projection 3D available with you, the callings and all the rest of the story is just similar to what you are doing with two-dimensional plots. Let me give a couple of more examples for these kind of for these plots. And further, by the way, we can use if I just use the layout, for example, if I'm right now I'm using the layout set by Seaborn. I can use a different layout, for example, plt dot style dot use. Maybe I can use a different style, maybe classic, and then the things will look like different in a different way. So, and you can have a lot of styles here. I mean, you can have a lot of styles. Let's check all the styles and just change the styles and see the look and feel. So plt dot style style dot available. So let's see. Oh, there are so many: dark background, fast, ggplot, Seaborn bright, Seaborn colorblind, and several of those. So many of them. So let's use, for example, this. Let's use this one. Let's use this one, and let's see how the plot looks like. Let's use this one. Just do. So now we have, oh, we have a really different look and feel of, but just changing the style, we have this particular look and feel. Oh my God, that's awesome. Anyways, you can play with all these kind of styles and all the stuff if you want. I'm actually moving towards another example of a 3D plot in which we are going to actually use a 3D scatter plot. So by default, I'll be using the Seaborn layout. So let's do some plotting using the scatter plot. Again, I will be using figure as plt.figure. That's my figure. And we'll be using axis as figure.gca, whatever the current whatever the current figure is, and the projection type is 3D. That's our projection type. So now what we really do is we have, let's say this X data is, let's say we have 100 points. Let's say we set 100 points. Let's say our X is simply is np.random.rand. How many of those? Let's say n of those. Let me, this is not rand n, this is not normal random distribution. This is the uniform random distribution. I'm generating n of n points. And let's have this to start with, let's say 32, and end with, let's say, let's start with this in this particular range, just to set that this particular range, plus 23. So it will start from really 0 and go to 23. It basically that will so basically I basically want to generate random numbers starting from 23 and ending at 32, and this basically will handle all that stuff for me. Next, let's say want to generate some other random data. Let's say another data, maybe and let's say right now we have like right now let's scale the data from 100 to everywhere, and np.random all these points, and let's say we have this as y, and let's generate a z as well, because we are going to do a three-dimensional plotting. Let's do a z as well. So the z is for example, let's start it by maybe minus 25, for example, minus 25. So that's the upper limit, or plus, let's say this is 50, and asterisk np.random.rand n, and maybe now we add or we just subtract a 50 out of it, and these are this is our x, y, and z data. Next, what we do really is let's say plot ax dot scatter, and x, y, and z. That's our values. The color we are going to give that is let's say red. Let me just write this as C is red. And the marker we are going to use is basically let's say the marker right now is just that. And here you can see that's the scatter plot. We may be able to change the size as well. So size is, let's say so let's have a size also. So in this case, we have a larger size. Yeah. So that's the plot. We may be able to generate the data, for example, in another way, just to have another. Let's generate more data, again randomly, and now let's use a different marker and different color just to see different kind of plots there. Let's use now blue color maybe, and let's use a triangle marker like this, and you'll be able to see two different kind of scatter plots in the same plot, like so. So that's what is happening. I mean, yeah, so that's completely a 3D scatter plot. Let me also introduce a surface plot for you in 3D, and then we will be primarily moving towards bokeh. Just let me give you one more example of this 3D plot, just a surface plot. We have seen a line plot, a curve plot, we have seen a scatter plot in 3D. Let me just use this surface plot as well. So let's say figure, let me make this a little bit higher. Let's say figure is plt.figure. That's my figure, let's say. And AX is again figure dot GCA, the grunt handle. And the projection type is, let's say, 3D. That's the projection type. Remember in our one of our earlier calls, we have imported this Access 3D. Yeah, so Access 3D. So we'll be using this Access 3D here as well, just to get some test data. There are some test data available in these Access 3D already. So let's use that. So let's get some test data using this Access 3D dot get test data, get test data, some data that is available. Let's set certain attributes, and if we just run that, we'll be having some test data that is available. Next, what we do is we say, okay, plot surface. That's a surface plot with X, Y, and Z as data. We can set our color map here. The color map is, let's say, cool, warm. Let's say that's our color map. And if we just run that, oh, it's nothing has shown. Why not? Access 3D has no attribute get test data. Why not? Maybe we have to import the Access 3D with, we have to import the Access 3D with smaller those. So let's from MPL toolkits dot mplot3d import Access 3D, Access 3D smaller, this one. So after importing that, let's use that AXES3D and get test data. Now it should work. It should work. It has worked. Oh my god, you see that surface plot here? Let me just, that's a surface plot. I mean, this is X, Y, and that is Z. That is completely a surface plot. We can set the alpha here if we want. Alpha equals, let's say, 0.5 just to see the opacity, and we can have this surface plot. We can have the surface plot completely in a different layout if we just change the style here. For example, plt.styles use, maybe we use a different style and get maybe a different look and feel of the same plot. Just let's say we use the Seaborn deep style just to see what it does. Just use that one. And you might see everything. No, it doesn't change anything. In this particular case, it doesn't change anything. What if we use here maybe, what if we use here BMH? What will it do if we use the BMH? Let's see. In this particular case, it is getting the same thing. I mean, that's somehow strange. Now you get a different kind of curve just by having this attribute different, by generating a different kind of data. You may have, for example, this alpha value a little higher to see less opaque this figure. I mean, that is a surface plot. How cool is that? You can set the alpha value to exactly 1 just to see the plot in more fancy colors. Yeah, so that's it has generated some data, and XYZ is the data, and you just plot a surface, and that's the surface available to you. We can have more on this basically 3D visualizations, but right now I'm going to discuss basically a bokeh library that is very fancy and very handy to actually for browser kind of plottings and interactive plots. More 3D plottings, more Seaborn, more Matplotlib, more pandas, and all that stuff is basically available in detail, in full length, in our full-fledged course at AI Sciences. So do enroll that course if you really want more detailed treatment of all these subjects that you're seeing here. So now I am moving towards Bokeh. Bokeh library, basically, both the Matplotlib and Seaborn libraries, they were static. Means whatever plot you generate, that is there. You cannot play with it. You cannot interact with it. Although the Bokeh actually generates a plot that is interactive. You can play with it. You can do interactions with that plot and stuff like so. So let me actually start with Bokeh. Just with an example. So let's say from bokeh.plotting import, let's say figure output file where you want your output file to reside and show function. Let's do that. So that happens. Now let me set the output file name, because the output here is always an HTML file. It generates a plot in HTML format, in a separate HTML, or sometimes in the same notebook, depending upon how you set your output file. So that's our output file. Let's say demo.html. Let's generate an object of figure. Here this figure is imported from Bokeh plotting. It is not the figure it is not the figure that you have seen earlier as plt.figure. It is the figure from Bokeh. So figure, then inside the figure, let's have this function. So inside the figure, let's have some of these properties of that figure. Let's say we need plot width as, let's say, 800. Let's say that's our plot width. Let's say we have plot height. Let's say HEIGHT height. Let's say that is maybe 400, and the title of this particular plot, let's say that title is line. And what we next do is p.line. That's the object that creates basically the figure, and now we are going to give the content inside that figure. So we want to generate a line plot, for example, and let's have x coordinates as 1, 2, 3, 4, and 5. These are the x coordinates. Let's say the y coordinates are basically 6, 7, 8, 9, and let's say 10. And we can also set some properties here. Width, let's say line width is 2. Let's set some properties here. And then at the end, once you have annotated all your object of type figure, then you have to call a show function on this object to just get it running. So now this will open up as demo.html in browser, And not only that, you can interact with this plot. See here, I mean, there are a lot of controls here. For example, um, zoom. You can just do the zoom, and you can just go and see what is happening. You can have the field zoom as well. If you just do that, you can save the figure. You can reset all the figure. I mean, yeah. So you can interact. So the basically the most powerful thing is that you can interact with that plot. You can set color bars here. In for example 3 dimensions, you can rotate the plots, and you can see the surfaces in several angles. Yeah. So that's about the interactive plotting. Let's see a couple of more examples in Bokeh just to get comfortable with Bokeh. And so let's see some more examples. Let's say, by the way, there you can have these line plots, you can have these circle markers or circle plots, you can have these triangle markers, all that you have seen in Matplotlib. There's a support there in Bokeh as well. So for example, let me generate a figure with plot width, let's say plot width as let's say 800. Let's say that's plot width. Then we have, let's say, plot height. Plot height, HEIGHT. Plot height is, let's say, 1000. And let's say the title of the plot is, let's say, example. Let's say that's the title. You can have another title. You can have axis label of that plot. Let's say that is X, and you can have the y-axis label. Let's say Y. The purpose here is to show you that you can basically annotate all your plot in several different ways if you want. So that is, let's say, a figure, and let's generate some data. Let's say X is np.len space maybe 0 to 10 maybe, and let's generate a 30 points. Let's say that is my X. Then Y1 might be np.sinx. Y2 might be np.cosx, and further we can have now p.line, for example, that will give a continuous or solid plot with, let's say, x, y1, and we can have legend here. We can specify the legend as sinx. That's our legend. We can have p dot, for example, circle in form of the circle markers, and we can have, let's say, xx, and we can have legend here, x itself. And we may have further properties. For example, if we have circle, we may want to fill its color with let's say some color, let's say green, and we may want to set the size of the marker if you want, really. Yes. Next, let's use triangle marker as well. Triangle. So triangle X. Let's use Y2 maybe. Let's use Y2. And let's have legend as cos x, and yeah, we can have, for example, size equals 3, and finally let's show the plot. So let's see what it does. Yeah, so it basically it actually goes to this. Why it is actually going to use all these legends here? So I guess I have done some mistake in setting the legend. Legend is x and x, that is circle, and the legend is simply x. So yeah, in this particular circle case, I'm getting let's say y equals x. I'm getting something wrong. Yeah, so I guess this is relatively more okay. But you can see here, for example, this is a line that is going there, and you can, for example, zoom to different areas to just see what is happening. And this is what is happening basically. The size of triangle is really small. You can have larger sizes. For example, maybe you have this size as 10, and you get a plot that is more visual in terms of these sizes. You can have different colors as well if you want. Yeah. So, but the main goal is basically you can play with it. You can see, you can zoom, you can save the figure and all that stuff if you really want. So yeah, so that's bokeh. We can have grid plots as well. In grid plots, you can combine, in bokeh grid plots, you can combine different plots together as one shape, and you can play with all of them just once, or if you want to play them individually, you can do that. You can set the properties of grids and all that stuff. So I basically end here. The second part of this video, I end the video here. Actually, there is much more detail to talk about that we will be discussing. As I mentioned again and again, we'll be discussing all these contents that you have seen. You have just seen the snapshots of the contents. We are going to discuss that in detail in a bit more length in our full course at AI Sciences. So if you like this content, if you like this video, subscribe our channel, like our content, and share with your friends, and do press the notification button so that you get the notifications for our upcoming material, and you'll get notified in time. So, and by the way, do enroll our full course. It is full of fun, and you will see much more details than you've seen here. You might be finding that course really interesting and helpful and useful. So, but anyhow, good luck.